Yep, that's right. The dream is over once more, and school holidays have concluded. It's time to go back to school. But dry those eyes because we have no time for tears right now. We've got work to do. We are going to learn about 2D vectors in the Extension 1 HSC course today. This lesson was frankly too much excitement for one video in its entirety, so I've split this up into two. Part 2 will be uploaded in probably about a week, so if you're keen to see that, maybe consider subscribing to the channel and then you'll see it when it's uploaded. Okay, I'm going to take you through the first few concepts of vectors in Extension 1, starting off with just what a vector is and some basic calculations, and then whatever I don't get to today, I'll finish off next week. So let's kick off with what the heck even is a vector? Okay, so to start this off, we're going to talk about the difference between an object's speed and its velocity. Okay, they sound like two very similar things. Speed is really just how fast an object is traveling, measured in kilometers per hour, for example. The difference between speed and velocity is that velocity also has direction, okay? Velocity can be positive if you're going forwards, and it can be negative if you're going backwards. Okay, so speed is referred to as what's called a scalar because it only has a magnitude, a how much. When you have a how much and which way, so you have a magnitude and a direction, you get what's called a vector. So there are a few things in this course that we're going to define as vectors. Forces, for example, are vectors. Velocity is another good one. For today, we're just going to keep it generic and just look at vectors, and then we'll look at applications later on in the course. Okay, so if it has magnitude and direction, it qualifies as a vector, and it can be studied by us in Extension 2 because we are just so blessed. Okay, let's look at some notations and terminology regarding vectors. So we have a vector here. We can see it has a length, which is the length of the line, and it's got a direction indicated by the arrow. Now, our notation for this vector is going to be a letter with what's called a tilde underneath. So when you see that squiggle underneath a letter, that indicates that that letter is actually a vector. So we can write V with a squiggle underneath, or we can write this as OA with an arrow above. Okay, O being the starting point, the origin, A being the end point, and it's going from O to A, and that's what the arrow indicates. We can also write this vector using what's called column notation. We can write this as the vector 2, 3. That's because this vector, this green line here, it's going 2 units across and then it's going 3 units up. Or when you start this vector from the origin, you can see that the vector points to the coordinate 2, 3. Okay, so the top number is the x, it's how far left or right. Bottom number is your vertical component, up or down. Very straightforward. Okay, two vectors are considered to be equal if they have the exact same magnitude and the same direction. Same length and same direction means they are the same vector no matter where they are. So for example, this vector here, BC, even though it's in a different part of the quadrant plane, it still has the same length and it has the same direction. So these two vectors are equivalent, and we can write OA equal to BC. Okay, the terminology here is that this vector here in the middle, starting from the origin, is called a position vector. Okay, so position vectors start from the origin, and ones that are located elsewhere are called displacement vectors, or free vectors is what they're sometimes called. Okay, if two vectors have the same direction, but not necessarily the same length, they're called parallel, just like with parallel lines. So this vector here, PQ, even though it's not the same length as the red and green line, it does have the same direction, so they're parallel, and we can write OA parallel to PQ. Okay, so parallel, all about direction. We don't really care about magnitude. Okay, back to our OA vector here, 2, 3. If we take a vector and multiply it by a negative, it's going to keep the same length, but it's going to reverse the direction. So if this is OA, 2, 3, as shown before, if we multiply that by -1, we get the same length, but we turn around and have the opposite direction. Okay, so it's just the other half of the straight line, I guess. So we can write -V is equal to U with our vector notation. And if you have a vector that's got a length of 1 unit, we call that a unit vector. So when your magnitude is 1, that qualifies you as a unit vector. So right here is an example V. This length right here, just trust me, is 1 unit. So that makes V a unit vector. Our notation for a unit vector is we give it a little hat. So the squiggle on the bottom means vector, and the little hat on top means unit vector, which means it has a length of 1. Okay, component form. This is another way of writing vectors. We're just going through all the terminology now, and then we can use them all later on in examples and get more confident. But I'm just showing you all the ins and outs, basically. So starting off with our horizontal and vertical unit vectors, which are called I and J. So that's 1 unit across for I, and that's 1 unit up for J. we can then write vectors in terms of these components. So if you have a vector AB, like for the example from the previous slide, that was 2, 3, we can write that as the x times the I unit vector plus the y component times the j unit vector. Okay, this is called component form. It means you can write it out horizontally rather than vertically, save some space, can be a bit neater, and you'll quite often see exam questions written in this form, so it's good to be aware of it. So yeah, just whatever's with your I is your horizontal component, and whatever's with your j is your vertical component. It's the exact same thing. Very straightforward. Okay, here are two vectors. We are going to write them in column form, and we're going to write them in component form for both of these, starting off with example 1. Okay, on the left here, we have a vector starting from the origin. It's going 3 to the left, and it's going 2 down. So it's got a -3 horizontal component and a -2 vertical component. So its column vector would be -3, -2. 3 to the left and 2 down, just like you're doing gradient. Very straightforward. Over here, no, we're going to then say we can write that in component form by giving the x value, the I unit vector, and then putting the vertical component, the -2, with the j unit vector. So x goes here, y goes here, and that's our component form. Okay, over here, our vector is not starting at the origin, so it's called a displacement vector as opposed to a position vector over here. Starting over here, we are going 1, 2, 3, 4, 5 units across, and then we're going 2 units up. So we have an x component of 5 and a y component of 2. So there's our vector in column form. Then once again in component form, we're going to have 5 and 2 with our unit vectors I and j. So we have 5i and then we have 2j. And because that 2 is positive, we're going to write plus 2j. Whereas over here, the 2 is negative, and that's why there was a minus there, if that's not already obvious. Okay, cool. So there's notations. There's how to write them out as columns and in component form. Let's move on to the next one. We have 2 points, A and B. 1, 4, and 3, 2 are our coordinates of A and B. We are going to draw a displacement vector for AB. So remember the difference between a displacement vector and a position vector. Displacement can be anywhere. Position has to start at the origin. So we have, there's our displacement vector starting from 1, 4 up here, going down to the point B, which is 3, 2 right there. So 1, 4 here, 3, 2 there. So there is our displacement vector. Now to make that a position vector, we're going to keep the same length. We're going to keep the same direction. We're just going to move this starting point. Instead of starting at 1, 4, we're going to start down here at the origin, and it's going to look like this. So the blue is the displacement, can be anywhere, and the green is the position starting at the origin. Now we're going to draw a third one. We're going to draw a displacement vector, which represents the negative version of these two vectors, so minus AB. Reminder from before, I showed you guys that when you take a vector and multiply it by a negative, all it does is just reverse the direction and it keeps the length the same. So we're gonna have a third line segment. Doesn't matter where you put it, it's just gotta have the same length as the green and blue lines, except the direction has been reversed, so the arrow goes this way instead of that way. Okay, so pretty basic so far. We're just working with our training wheels on now before we start riding 26 miles. Let's now start talking about golf, because golf is a good introduction to how we actually take two vectors and add them together or subtract them. Let's say I was playing golf and let's say I was really good at it, which is a bit of a fantasy, and we're hitting a golf ball on this vector, some northeast direction, with a magnitude of 1,000 newtons. Now, the ball may not necessarily land at the end of this vector because there are other things to consider. Like, for example, there could be a wind force of 300 newtons going in a sort of opposite direction, sort of like southwesterly thingo. Okay, so if you have the force of my golf swing putting us up here, but you have the force of the wind sending us this way, well, where's the ball going to land? Well, we're going to put that wind vector just at the end of the golf swing vector, and then that is a good estimation for where our ball is going to land. So what's happening here is we are applying two vectors to one object. We have the force of the swing and we have the force from the wind. Applying two vectors is kind of like adding them together. We do the blue vector and then we do the red vector, and then we get our resultant vector, which is the dotted black line. So anyway, long story short is the black vector there is the result of adding the blue and the red together. So method one, if you want to combine two vectors, you can make a little triangle and find the endpoint, and that gets you your resultant vector. Another option is you can have these two vectors starting from the same points, and what these two make is half of a parallelogram. We've got two sides of a four-sided shape. if you fill in the other two sides, the resulting corner up here is going to be the endpoint of your addition vector. So from, again, the black line that I forgot to put in. So option 1, combine your two vectors by making a triangle. Option 2, make a parallelogram by setting them base to base and then fill in the rest. And either way, you'll get this endpoint here, which is the result of combining both vectors. That's the long story short. Okay, so some examples of adding vectors. When they're in column form like this, it's very straightforward. We've got 1, 3 plus 2, 1. All you got to do is 1 plus 2 for the horizontal component, and for the vertical component, we're just going to do 3 plus 1. So we end up with just 3 on the top and 4 on the bottom. Easy peasy. So when you got numbers, it's easy. When you got pictures, you got to be a bit more clever. Like I said, geometrically, this is either completing a triangle or completing a parallelogram with the two vectors. So you can either put this green one up here and make a triangle, and that red dotted line will be 3, 4, as we can see, 3 across, 4 up, so it works. Or like I said, you can put them at the base and then complete the parallelogram, and you get this point up here, which is 3, 4 once again. So you can use either of these. I use both depending on the situation. Sometimes one is easier than the other, but that's the two ways you can geometrically make sense of adding two vectors together. Okay, now for subtraction, it's a bit trickier. There's some stuff to remember here. Numerically, very straightforward. We're just going to do 1 minus 2 is minus 1 for the x components. For the y components, 3 minus 1 is 2, and so that is our resultant vector. Now, geometrically, what we're going to be saying here is that if you're doing a minus b, what you're going to get as your result is a vector from the endpoint of b to the endpoint of a. That dot point there is probably the most important thing to remember for this first part of the lesson, because it is so commonly used and assessed. So the thing to memorize here is that if you want a minus b, all you need to do is a vector from b to a. I'm going to say that again because it's so important. A minus b is the vector from b to a. Hopefully that's memorized now, and we can use it and apply it in some further examples. Here's a proof if you don't believe me. There's a and b, and a minus b, we're going from the endpoint of b, which is the green part here, to the endpoint of a, which is the blue part here. That red vector, would you believe, goes 1 to the left and 2 up, which was the resulting vector from our subtraction, minus 1, 2. Okay? Third and final time, the vector a minus b is the vector from b to a. Easy peasy, there's your shortcut. Thanks for coming, subscribe. Okay, let's do some examples. We've got two vectors here, a and b. First thing we're going to do is we're going to add them together. You can use either of the methods I showed you before. I can't remember what I did, so let's see. I'm guessing I'm going to put them base to base. All right, there's A, and there's B, base to base. And now if we either complete the parallelogram or make a triangle, either way, you're going to end up with this point here. And so that green vector there is the result of A and B plus together, because we're either putting B up here and making a triangle to get the endpoints, or we're completing the parallelogram to get the endpoints, and then the green vector is our result. All right, that's beautiful. Now we'll do A minus B, and hopefully you were listening when I said it 4 times before. I said that the shortcut to getting the vector A minus B is you do a vector from B to A. And when I say from B to A, I mean from the endpoint of B to the endpoint of A. So we just go up there, and that red line there is A minus B. Now for the next one, if we want to do B minus A, we've got to do the opposite. We've got to do the vector from the endpoint of A to the endpoint of B. So it's going to be the same length as that red line, but instead of from B to A, we're going from A to B, so the direction is going to reverse. Like that. Oh, fancy animations. I'm so good at my job. All right, and now for the fourth one, we're going to do the vector A plus 2 times the vector B. Now, whenever you take a vector and you multiply it by a whole number, or just a number, I guess, this is called scalar multiplication. What's going to happen to this B is it's going to stay the same direction, but the vector is going to become twice as long. So vector A is remaining the same. Vector B has now been doubled in length. So instead of going down and across 2, it's going down and across 4. Okay? Now we do A plus 2B, once again, either making a triangle, making a quadrilateral. Either way, we are trying to get this endpoint here. And then from the starting point to that endpoint is our resultant vector of A plus 2B. So there you go. Now you know how to add and subtract vectors. You know how to multiply vectors by whole numbers, either geometrically or algebraically. Either way, it's piss. Okay, next example, we've got a shape. What do we call this? I guess that's a hexagon. Good counting. Okay, bunch of letters. We're going to find the resultant vector of adding AB and BG. Let's have a look. Here is AB and here is BG. Now, if I add this vector to this vector, what's it going to make? Well, let's complete the triangle. AB plus BG is going to be AG. Okay, so from this vector to this vector, completing the triangle, we get AG, which makes sense if you look at the letters. A to B plus B to G is just A to G, just the B is the midpoint, so it just gets cut out. I don't know if that makes sense. The next one, we've got EG plus AF. So EG is up here from E to G. AF is down here. Oh, would you look at that? These two vectors have the same length, but they have opposite direction because EG is going up there and AF is going down there. I don't know if it exactly looks like that on your screen. I think it's because I slightly warped the picture, but trust me, these two vectors are meant to be the same length but opposite directions. Now, when you add this to this, well, this is going up, this is going down, and because they're the same length, they just cancel out. So when you add a vector to its negative, it's like adding 2 to negative 2. They just cancel out. So the answer for B is just 0. Okay, now for question C, we've got GC minus BC. Let's have a look at that. GC is here and BC is here. Now, a cool trick we can use here is that this is BC, so why don't we just make this negative BC by just turning it around? Aha, okay. So again, BC was from here to here, so negative BC is just from here to here. It's really just CB. And now, if you're subtracting BC, you're really just doing the exact same thing as adding negative BC. What I'm trying to say here is that the shortcut is just GC plus negative BC, which is just CB. It's just going to be GB. So it's the resulting vector up here because we took the BC, which was going this way, we turned it around, and now this plus this makes that. I hope that made sense. It kind of made sense to me, but you're probably smarter than me. Okay, and question D, we've got GE going down here. We've got EF going up here, and then we've got FA going up here. Well, we did this, and then we did this, and then we did this. So there's our endpoint there. Our starting point is there. So our resulting vector is just from G to A. Okay, when you're applying multiple vectors and you're just going from tail to tail, you're just going to have your starting point to your end point, which is GA. Okay, there it is, nice and simple. Okay, let's look at a quick HSC question before we move on to the last part of today's lesson. We've got a band 3 from 2021 multiple choice. We've got two vectors, OP and OQ, -3, 1, and 2, 5. The question is asking us is what is PQ, the vector from P to Q? I'll show you two ways of doing this. I'll show you the geometric way, which is probably longer, and then I'll show you the algebraic way, which is a bit of a shortcut, which is way easier, which is what I would do, but it wasn't me. So here we go. We've got a graph here, correct? Okay, OP is going from O, the center, to -3, 1. So we're going 3 to the left and we're going 1 up. Yes, 1 up. 1 is a positive number, you idiot. Okay, and OQ is doing 2, 5. It's going 2 across and 5 up, and I wish I got a bigger axis, but it kind of fits. So we're trying to find the vector from P to Q. So from this point to this point. Well, there it is on the map. And now if we want to find the coordinate that it's pointing at, we just need to make this vector starting from the center to make it a position vector. So we'll move that green down here. And now we can see that green line, if you use your imagination a bit, is going 5 across and 4 up. So it must be option C. All right, that's the geometric way. Of course, you won't have an axis in your exam, and I really don't want to expect you to be wanting to draw this diagram for a 1-mark question. So the shortcut is that just, nope, it's not there. Okay. The shortcut is that the vector from P to Q, using the thing I taught you before, is that this is just the vector Q minus P. Okay, once again, Q minus P is the vector from P to Q. So we really just need to do this coordinate, subtract this coordinate, and we'll get our answer. 2 minus -3 is 5, correct? And then 5 minus 1 is 4. So there's the shortcut to get your answer C very quickly, which is why it was only a band 3. It's considered an easier question. So once again, the vector from P to Q is Q minus P. Simple as that. Now we can move on. All right, last part of today's lesson is all about the magnitude of a vector. And when I say the magnitude, I of course mean how long is it. So here's a vector from O to A, represented by an X component and a Y component. If you wanted to find out how long this line is, you would have to pass year 8 mathematics, so you know how to use Pythagoras, because we can just turn this into a right angle triangle, which has got a length here of x and a length here of y, and then the length of the red line, which is also known as a hypotenuse for the maths fans in the chat. We just do x squared plus y squared. We take the square roots, and then voila, you have your magnitude, your hypotenuse length. So that's why our formula for today, the absolute value of a vector is called the magnitude. It's how the length of the line. And it's just the square root of x squared plus y squared. It's just Pythagoras. Okay, some examples. Here are two vectors A and B. We're going to start off by finding the magnitude of A. So A has an x component of 1 and a y component of 5. So to find the magnitude, we're going to take those components, 1 and 5. We're going to square them, we're going to plus them, and we're going to take the square root. So 1 squared plus 5 squared is 26. So vector A has a length of root 26 units. For part B, we're going to find the vector B minus A with a bit of simple subtraction. Then we're going to find the magnitude of that vector, and we're going to square it. This may seem pointless now, but this is going to come into play in a later lesson. So start off B minus A. We're just going to subtract the two vectors. So B is 3 minus 2 for its components, and A is 1, 5. When we subtract those, we get 3 minus 1 is 2 for the top, and we get minus 2 minus 5 is minus 7 for the y component. So there is B minus A. Now if we take the magnitude of that, we're going to be doing, we're going to do 2 squared plus negative 7 squared. So we'll get 4 here, we'll get 49 here, so we get the square root of 53. And I'm now just realizing that I think I forgot to square this when I was doing my solution. So we should actually be taking this answer and we should be squaring it to get 53. So root 53 is not the correct answer, sorry. It's actually 53 once we square it. I forgot that, so I am a big dum-dum. I'm sorry. Okay, and question C is asking us for a unit vector in the direction of B. What that means is we want to take vector B, which currently has a length of something, and we want to make it have a length of 1. Okay, if you reduce a vector's length from whatever its magnitude is down to 1, it then becomes a unit vector. Okay, unit vector length 1. So to do that, the first thing we need to figure out is what is the length of B. So we'll find the magnitude of B using Pythagoras once more. X component of 3, y component of minus 2. Square those guys, add them together, and we get 9 plus 4 is 13. So vector B has a length of root 13 units. So if it has a length of root 13, how do we make it have a length of 1? Well, if you've got something that's like 10 meters long, and you divide it by 10, it now has a length of 1, yeah? So if you take an object's length and divide by that length, you'll make it have a length of 1. So the secret here is to find, sorry, the birds are going absolutely nuts outside. We've found the magnitude is root 13. If we take vector B and we divide it by root 13, that will now turn it into a vector of length 1. So we can just write this as 1 over root 13. That's our division right there, just multiplying by the reciprocal. It's just a nicer way of writing this. 1 over root 13 multiplied by B, and that right there is a unit vector, which is why it's got that little fancy hat on. Okay, fancy hat means length of 1. Oh my god, I'm tired. I haven't worked this hard in 6 weeks. Okay, two vectors u and v, for example 6. U has components 6 and 2. V has got components 2 and negative m, so it's unknown. Part A is to find a column vector representing 2 times u minus 3 times v. Okay, it's not too hard. Let's dive in. Let's take vector u and multiply it by 2. And we'll take vector v and we'll multiply it by minus 3. Just using horizontal component form just to make it a bit easier. So timesing these by 2 turns it into 12 and 4. Timesing these by 3 turns it into 6 and minus 3m. And now we just do our subtraction. So 12 minus 6 for the top will be 6. On the bottom we have 4, take away negative 3m. So we have 4 plus 3m. So 6 on the top, 4 plus 3m on the bottom. And that is our column vector representing 2u minus 3v. We did it. Amazing. Part B, find the values of m for which the magnitude of v, the second vector, is equal to 3 root 2. Okay, so let's start off by finding the magnitude of this vector, and then we're going to set this equal to 3 root 2, and then we'll solve it, see what we get. So magnitude, x component is 2, vertical component is negative m. So we're taking those two and we're squaring them. We're adding them together and we're taking the square root to find the magnitude. So this turns into 4. This turns into positive m squared. So we get the square root of 4 plus m squared. Now we're setting this equal to our magnitude, which is 3 root 2. And we're going to solve this for m. So let's probably start off by squaring both sides to get rid of the square root on the left. So when we square the left, square root goes away. 3 turns into a 9. Square root of 2 turns into a 2. And so we get 18 on the right because we get 9 times 2. Subtract 4 from both sides and you get m squared equals 14. And so then m must be the square root of 14. But don't you forget that plus minus, or you're going to lose a mark in the HSC and you'll bring shame to your family and throw yourself off a bridge. So plus minus root 14 is the answer to this question. Please don't throw yourself off a bridge. Okay, I think we're finishing off with an HSC question from 2020. It's another band 3, so it's not meant to be life-ruining by any means, but we're new to this, so let's see how we go. Bloody Blah starts at the origin, walks along 2, 3 vector, and then walks along 3, minus 2 vector, and then walks along 4, minus 3. How far from the origin is she? Okay, I'll let you have a think about this one. Maybe do some drawings or some scribbles, or maybe you already know the answer. You're smarter than me, you're quicker than me. Congratulations. All right, that's enough pause. All right, so what's happening here is Maria is applying 3 vectors to herself, which is a strange sentence. So what's happening is, if we want to find the resultant vector from where she's starting to where she's ending, kind of like we were doing before with the golf ball and the wind or that weird hexagon thing, we just need to add these 3 vectors together, and that will give us our resultant vector from our starting point to our finishing point. Then we can just find the length of that vector, and hopefully it's one of these 4 answers, and then we get a mark. So like I said, we're going to find the resulting vector by adding them all together. Am I actually drawing this? Oh my god. All right, 2 across, 3 up. That's great. And then the next one is 3 across, 2 down, like that. And then the last one is 4 across, 3 down. Great. So this vector plus this vector plus this vector equals this vector. So to find this red vector, as I said before, we're just going to add these 3 together. So we've got this one plus this one plus this one. If we add the horizontal components together, we get 2 plus 3 plus 4, which is 9. Oh my god. The vertical components are 3 plus negative 2 plus negative 3, which is minus 2. So we end up with 9 for our x component and minus 2 for our y component. That is the vector shown in red here. It's going across 9 and it's going down 2. So the algebra and the geometry are matching up perfectly. Now we'll just find the length of the red line shown here by finding the magnitude of this vector by taking 9 and minus 2, squaring them, add them together, and then take the square root. So we got 9 squared plus negative 2 squared. We get 81 here, we get 4 here, so we get 85. And so it must be the square root of 85. If you got that as well, amazing work. You're a god. I'm so proud of you. Okay, I think that might be all for today. Okay, yeah, there it is. Great. All right, that's part 1 done. I'll do the next half of this topic very soon, probably on this channel. So hit subscribe and stay tuned to learn more about vectors in the very near, probably not distant future. Okay, thank you very much, and welcome back for 2024. I've missed you so much.